So let's add a very critical concept to this, the so-called Coriolis effect. As we said, we are on a moving Earth on a day-to-day basis. We don't feel it, even though on the equator Earth is moving at some 1600 miles per hour. Why? Because we are on the rotating frame. But how do we learn about it? Very simple way to start would be to think about a merry-go-round, where you can actually be standing on the merry-go-round or outside and see what's happening on the merry-go-round. The rotational effects are easily understood in this way, but again, the sphere makes a big difference. On the merry-go-round, the rotational effects are constant. When we go on the sphere, it turns out the rotational effects are critically dependent on which way you move and at what latitude you are moving. Okay, so let's say you are standing here and there is your friend standing over there. You're in the red shirt, green shirt. The merry-go-round, when you look from the top, is going in the counterclockwise direction. So you started at point A, and then after some time you're at point B, and your friend was here, and then he or she, it looks like a she, moved over there. What did you do? When you were at this point, you threw a ball at her. But because you are moving in this direction and she is moving in that direction, for you it looks as if the ball didn't go in a straight line but went in a curve. Whereas if it's your mother that's standing outside, she will not see any curving at all. She will see that you threw the ball to your friend or your sister and she caught the ball. Whereas because you're on the merry-go-round and because you are moving and your friend is moving, you feel as if the ball curved. This is the essential concept of Coriolis. Because we are on a rotating planet, if we move on long distances, this planetary rotation effect becomes important and it begins to tilt things away from the direction of motion. Here the direction of motion of the ball when you threw it was towards your sister, but it looks like it curved. It boils down to a very simple thing before we look at the details. Everything in the northern hemisphere gets deflected to the right of the direction of motion in the northern hemisphere. To the right of the direction of motion. Right? Earth is hanging in space, and if you look from the South Pole, things are going in the opposite direction. So Coriolis effect is also in the opposite direction. So everything in the southern hemisphere gets deflected to the left of its direction of motion in the southern hemisphere. To the left. To the right in the northern hemisphere of the direction of motion. To the left of the direction of motion in the southern hemisphere. This is something to remember. I will show this with animation and so on in the next videos. I want to stop it here because I want you to stare at this merry-go-round a little bit and try to get the concept of where the Coriolis effect comes from. Why do we call it Coriolis effect and not Coriolis force? Because it's actually not accelerating the projectile or the ball that you threw. It is just changing the direction. So it's called an apparent force. But you will see that as we develop the equations of motion and so on, we forget this simple fact that it's an apparent force and it's effective only because you're in a rotating framework. It's a Coriolis effect, but we will loosely end up using terms like Coriolis force. It becomes very critical because it creates for some very unique flow features on a rotating framework. Again, to repeat, as I said before, the fact that things are stratified in the ocean and stratified in the atmosphere, and there is Coriolis effect because of rotation, we begin to get some very unique circulation patterns which are very critical. But everything comes down to understanding this apparent effect because you are on a merry-go-round. It gets complicated on a sphere, as I said, but we'll understand that soon enough.